Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast emptiness between stars, where ancient objects drift on trajectories that shouldn't exist. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need all moment of stillness too. And to those who've already joined along, thank you. In the cold between star systems, where temperatures hover just above absolute zero at minus 454 degrees Fahrenheit, objects drift for millions of years without purpose or destination. They tumble slowly through the cosmic dark, their surfaces sculpted by radiation and micrometeorite impacts, carrying within their crystalline structure the chemical signatures of worlds that died before Earth was born. These wanderers move according to laws written in the language of gravity and momentum, following paths so predictable that astronomers can calculate their positions centuries into the future with mathematical precision that would make a Swiss clockmaker weep with envy. The space between stars stretches so vast that light itself grows weary crossing these distances. A single cubic meter of interstellar void contains fewer than one atom, making it more empty than the most perfect vacuum humans have ever created in their laboratories. Yet through this near-nothingness, ancient debris from stellar explosions and planetary collisions drifts with the patience of geological ages, each fragment carrying stories written in isotope ratios and crystal matrices formed in the hearts of dying suns. Most of these cosmic wanderers follow trajectories governed by the gentle gravitational influence of nearby star systems, their paths curving in long, lazy arcs that span millions of years. They accelerate toward massive objects, slow as they climb out of gravitational wells, and coast through the empty regions where space-time lies relatively flat and undisturbed. Their motion obeys Newton's laws with the reliability of sunrise, creating orbital equations so elegant that astronomers can predict their behavior with confidence bordering on arrogance. Yet sometimes, very rarely, one of these ancient travelers enters our solar system carrying a secret that makes the equations whisper lies. Its trajectory bends in ways that gravity alone cannot explain, accelerating when it should coast, curving when it should fly straight. The numbers refuse to balance, like a bank statement that insists 2 plus 2 equals 5. The mathematics sleep fitfully, disturbed by observations that don't fit the comfortable patterns of celestial mechanics that have governed astronomical calculations for 3 centuries. On October 19, 2017, at precisely 7:21 Universal Time, a robotic telescope atop Haleakala volcano in Hawaii captured photons that had traveled 93 million miles from an object smaller than a city block, an object that had been drifting through interstellar space for perhaps tens of millions of years. The Panoramic Survey Telescope and Rapid Response System, known by the acronym PAN-STARRS, collected these ancient photons in its digital sensors, converting starlight into data streams that would flow through fiber optic cables to computers programmed to search for anything unusual moving against the background of supposedly fixed stars. The light carried information encoded in wavelengths and intensity variations, data that would soon challenge everything astronomers thought they understood about visitors from other star systems. The object's brightness flickered with a regular rhythm, suggesting it tumbled end over end as it traveled, its elongated shape alternately presenting its broad side and narrow profile to Earth's patient observers. These brightness variations painted a portrait of something profoundly alien not in the sense of extraterrestrial intelligence, but in the deeper sense of belonging to a different stellar neighborhood entirely. The Discovery team, led by Robert Warwick at the University of Hawaii's Institute for Astronomy, named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. The name carried gentle poetry, but also prophetic weight that would only become clear in the months that followed. This cosmic messenger had indeed arrived first, the inaugural member of a new category of objects that astronomers would learn to call interstellar visitors, but it delivered questions rather than answers, riddles written in the language of orbital mechanics and hidden accelerations. The object moved with the unhurried patience of geological time, yet beneath its apparent calm lay mysteries that would keep scientists awake for years, staring at computer screens filled with calculations that refused to resolve into comfortable certainties. Every additional observation seemed to deepen the puzzle rather than solve it, as if the universe had decided to send humanity a cosmic riddle wrapped in the mundane disguise of rock and ice. Initial orbital calculations revealed that Oumuamua approached the solar system from the direction of the constellation Lyra, traveling at a speed that marked it unmistakably as an interstellar interloper. No object born in our solar system could maintain such velocity without the gravitational assistance of planets or the propulsive force of outgassing from a comet's nucleus. Yet, as observations accumulated and orbital models grew more precise, astronomers discovered something that shouldn't have been possible according to everything they thought they knew about how objects move through space. The visitor was accelerating away from the sun, not dramatically, but measurably, consistently, in ways that violated the elegant simplicity of gravitational mechanics. The acceleration was tiny, about a 10,000th of Earth's surface gravity, but persistent enough to accumulate into a trajectory that curved more sharply than pure gravitational dynamics could explain. It was as if some invisible hand gently pushed the object away from our star, applying force so subtle that it barely registered in the most sensitive instruments, yet consistent enough to bend the path of a mountain-sized rock over the course of months. In the darkness beyond Neptune, where sunlight grows thin and the solar wind barely whispers, Oumuamua continues its journey outward, carrying its secrets toward a destination it will never reach in any human lifetime. Its path through space draws an elegant curve that mathematicians cannot quite reproduce with their most sophisticated models, a gentle reminder that the universe still holds surprises for those patient enough to watch and humble enough to admit what they do not understand. The object fades now toward invisibility, its reflected sunlight growing too weak for even the largest telescopes to detect, leaving behind only questions that drift through the scientific literature like cosmic debris, waiting for the next interstellar visitor to arrive and either confirm or contradict the mystery of trajectories that don't add up. The first stranger arrives without fanfare, a dim speck of reflected sunlight sliding across the star-filled darkness like a grain of sand on black velvet. For weeks, this wanderer has been approaching the inner solar system, growing incrementally brighter as it draws nearer to the sun, yet still so faint that only the most sensitive automated telescopes can detect its presence against the cosmic background. Its light carries the chemical fingerprints of minerals forged in stellar furnaces that burned out before our sun ignited. Isotope ratios that speak of planetary formation processes in alien star systems whose names exist only in astronomical catalogs. On that October morning in 2017, when the Pan-STARRS telescope captured the photons that would announce humanity's first confirmed interstellar visitor, the object designated A2017-U1 moved through space with a velocity that immediately marked it as foreign. At over 26 kilometers per second relative to the Sun, it traveled faster than any comet or asteroid born within our solar system could naturally achieve. This speed spoke of origins measured not in astronomical units, but in parsecs, distances so vast that light itself requires years to cross them. The discovery process unfolded with the methodical precision that characterizes modern astronomy. Yet beneath this routine lay a profound moment in human history, the first time our species had definitively identified an object from another star system passing through our cosmic neighborhood. Robert Verick, examining images from the previous night's observations, noticed a point source moving against the background stars at an unusual rate. The object's motion appeared inconsistent with the orbital characteristics of known solar system bodies, suggesting something far more exotic than another piece of asteroidal debris from the Kuiper Belt. Within hours, observatories around the world began tracking this mysterious visitor, their telescopes turning toward coordinates calculated from the initial Hawaiian observations. Each facility added its own photons to the growing database of measurements, building a portrait of an object unlike anything previously catalogued in astronomical surveys. The European Southern Observatory's Very Large Telescope in Chile captured spectra revealing a surface composition reminiscent of metallic asteroids, while observations from the Gemini Observatory suggested unusual rotational characteristics that would soon prove even more puzzling. As the days passed and more observations accumulated, the object's hyperbolic trajectory became increasingly clear. Unlike comets and asteroids bound to our sun by gravitational chains forged billions of years ago, this visitor followed an open orbit that would carry it past our star and out into interstellar space, never to return. Its path curved around the sun like a slingshot maneuver executed by cosmic accident, gaining speed as it fell inward through the solar system's gravitational well before being flung back toward the darkness between stars. The International Astronomical Union, faced with humanity's first interstellar visitor, had to invent new nomenclature to properly classify this unprecedented discovery. Traditional comet and asteroid designations proved inadequate for an object that belonged to neither category in the conventional sense. After considerable deliberation, the IAU created a new classification system, designating the visitor as One-Eye Oumuamua, the first object in the I category, reserved for confirmed interstellar interlopers. The Hawaiian name carried layers of meaning that seemed almost prophetic in retrospect, in the native language of the islands where the discovery was made. Oumuamua translates roughly as scout, or messenger from afar arriving first, suggesting both the object's origins in distant space and its role as the harbinger of future interstellar visitors. The name also carried cultural weight, acknowledging the indigenous people whose lands hosted the telescope that made the discovery possible. A gentle reminder that even the most cosmic discoveries remain grounded in terrestrial contexts. Yet, as astronomers celebrated this historic first detection of an interstellar object, subtle anomalies began emerging from their increasingly precise measurements. The visitor's brightness varied in ways that suggested an extremely elongated shape, tumbling end over end as it traveled through space. Its light curve painted a picture of an object perhaps 10 times longer than it was wide, spinning with a period of 7.3 hours that remained remarkably stable throughout the observation period. More troubling still were the tiny discrepancies appearing in trajectory calculations as observational precision improved. The object's path deviated slightly but consistently from the elegant curves predicted by pure gravitational dynamics. These deviations were small, requiring the most sophisticated orbital analysis software to detect, but they accumulated over time into a pattern that couldn't be explained by measurement error or computational limitations. Something was pushing Oumuamua away from the sun with a force so gentle it barely registered in astronomical instruments, yet persistent enough to alter the object's trajectory in measurable ways. The acceleration was roughly 10,000 times weaker than Earth's surface gravity, comparable to the weight of a paperclip pressing on your palm, but applied consistently over months to an object weighing millions of tons. This tiny force could bend even the most precisely calculated orbital predictions. The mystery deepened as astronomers searched for conventional explanations. Comets routinely experience non-gravitational accelerations as solar heating sublimates volatile compounds from their surfaces, creating jets of gas and dust that act like tiny rocket engines. Yet, Oumuamua showed no visible signs of outgassing, no coma of evaporated material, no tail of dust swept away by the solar wind, no spectroscopic evidence of water vapor or other volatiles escaping from its surface. The visitor appeared to be accelerating without any obvious mechanism to explain the phenomenon, challenging fundamental assumptions about how objects behave in the vacuum of space. As it continued its journey outward past Mars, then Jupiter, growing ever fainter and more difficult to observe, Oumuamua carried with it questions that would puzzle astronomers for years to come. Mysteries encoded in orbital mechanics that refuse to conform to the comfortable predictability of Newtonian physics. In observatories scattered across 6 continents, astronomers bend over computer screens filled with columns of numbers that refuse to behave according to the ancient laws of celestial mechanics. Each measurement carries the precision of atomic clocks and laser interferometry. Coordinates calculated to 15 decimal places. Velocities measured with accuracies that would have seemed magical to Newton himself. Yet beneath this mathematical sophistication lies a growing unease. A sense that the numbers whisper secrets that challenge 3 centuries of gravitational theory. The calculations begin with the fundamental assumption that objects in space move according to gravitational forces and nothing else, unless they happen to be comets actively shedding material into the solar wind. Mass attracts mass with a force proportional to the product of their weights and inversely proportional to the square of the distance between them, a relationship so reliable that space agencies use it to fling robotic explorers across billions of miles with pinpoint accuracy. These equations have guided spacecraft to distant planets, predicted the return of comets with clockwork precision, and revealed the existence of dark matter through subtle gravitational influences on galactic rotation curves. For Oumuamua, however, the mathematics refused to sleep peacefully. Initial orbital calculations based on the first week of observations suggested a classic hyperbolic trajectory, the path of an unbound object falling toward the Sun from interstellar space before being accelerated back toward the cosmic deep. The curve appeared elegant in its simplicity, a textbook example of gravitational mechanics played out on a solar system scale. Astronomers felt the satisfaction of watching universal principles operate exactly as theory predicted they should. But as observation periods lengthened and measurements accumulated, tiny discrepancies began emerging like cracks in a perfectly smooth surface. The object's position deviated from predicted coordinates by amounts measured in arc-seconds angular distances, so small they would be imperceptible to human eyes even with the aid of powerful telescopes. Yet, for astronomers accustomed to predicting planetary positions decades in advance, these seemingly insignificant deviations represented fundamental challenges to their understanding of how objects move through space. Marco Micheli of the European Space Agency led the team that first quantified these anomalous accelerations, analyzing observations spanning several months to build a comprehensive picture of Oumuamua's trajectory. Using data from telescopes around the world, including NASA's Hubble Space Telescope and the European Southern Observatory's Very Large Telescope, the researchers constructed orbital models with unprecedented precision. What they discovered defied conventional explanation. The object was accelerating away from the Sun at approximately 5 to 10 Drauren 6 meters per second squared, a force so gentle it would take several minutes to accelerate a falling leaf from rest to walking speed. This acceleration might seem trivial by terrestrial standards, but applied to an object weighing millions of tons over the course of months, It accumulates into trajectory changes measured in thousands of kilometers. The effect resembles what astronomers observe in active comets, where sublimating ice creates jets of vapor that act like natural rocket engines, pushing the comet slightly away from its purely gravitational path. Yet, Oumuamua displayed none of the characteristic signs of cometary activity: no visible coma, no dust tail, no spectroscopic evidence of water vapor or other volatiles escaping from its surface. The mystery deepened as researchers considered alternative explanations for the observed acceleration. Solar radiation pressure, the gentle push of photons striking the object's surface, could theoretically account for small, non-gravitational forces. Sunlight carries momentum, and when photons reflect off a surface, they transfer this momentum to the reflecting object, creating a force that grows stronger as the object approaches the sun. For spacecraft with large solar sails, this radiation pressure provides propulsion for interplanetary missions that unfold over years or decades. Yet, when astronomers calculated the radiation pressure that Oumuamua should experience based on its estimated size and surface properties, the numbers fell short of explaining the observed acceleration by nearly an order of magnitude. The object would need to be far more reflective or much thinner than observations suggested to account for the trajectory deviations through radiation pressure alone. This discrepancy led to increasingly exotic hypotheses about the visitor's composition and structure, proposals that stretched the boundaries of what seemed physically reasonable for a natural object. The Yarkovsky effect, a subtle thermal phenomenon that can alter asteroid orbits over geological timescales, offered another potential explanation. When rotating objects absorb sunlight and re-radiate the energy as infrared heat, they experience tiny propulsive forces as thermal photons carry away momentum in preferred directions. This effect has been measured for near-Earth asteroids, where it causes orbital decay rates measured in meters per year over thousands of years of observation. But again, the magnitude of acceleration observed for Oumuamua exceeded what the Yarkovsky effect could reasonably produce for an object of its presumed size and composition. The thermal forces would need to be enhanced by factors that required increasingly speculative assumptions about the visitor's surface properties, internal structure, or rotation dynamics. Each potential explanation seemed to require its own set of unlikely coincidences or extraordinary physical characteristics. As weeks passed and Oumuamua faded beyond the reach of even the most powerful telescopes, astronomers found themselves confronting an uncomfortable truth. They had insufficient data to definitively explain the object's behavior using conventional physics. The trajectory anomalies were real, measurable, and reproducible across multiple independent analyses, yet no single explanation could account for them without invoking physical properties that bordered on the implausible. The numbers continued their quiet rebellion against gravitational orthodoxy, leaving behind equations that slept fitfully in astronomical databases, waiting for future interstellar visitors to either confirm or contradict the mystery of accelerations that shouldn't exist. Only later would astronomers realize that Oumuamua's strange behavior was not an isolated anomaly, but the first hint of a pattern that would challenge their understanding of how objects from other star systems behave when they wander through our cosmic neighborhood, carrying secrets encoded in trajectories that refuse to follow the ancient rules of celestial mechanics. Through the deep black of interplanetary space, a mountain-sized fragment of some distant world tumbles with the unhurried rhythm of a cosmic metronome, completing one full rotation every 7 hours and 18 minutes. This slow-motion dance has continued for perhaps millions of years, the object spinning end over end as it drifted through the emptiness between stars, its rotational period locked into a stable pattern by the subtle physics of angular momentum conservation. The tumbling motion speaks of ancient violence, perhaps a collision that shattered a parent body eons ago, or gravitational forces that tore material from a planetary surface during a close encounter with another world. As Oumuamua rotates, it presents alternately its broad face and narrow profile to Earth's patient observers, creating a light curve that rises and falls with mathematical regularity. When the object's long axis points toward Earth, its cross-sectional area appears maximized, reflecting more sunlight and appearing brighter in telescopic images. As rotation carries the narrow end into view, the apparent brightness diminishes, sometimes by factors of 10 or more. This dramatic variation in reflected light reveals an object with proportions unlike anything previously discovered in our solar system. The brightness measurements paint a portrait of extreme elongation, suggesting a needle-like form perhaps 400 meters long and only 40 meters wide, proportions that challenge conventional understanding of how natural objects form and survive in space. Most asteroids and comets maintain roughly spherical or potato-shaped profiles, their forms sculpted by gravitational forces that tend to minimize surface area and create relatively compact structures. Yet, Oumuamua appears stretched into a cigar-like configuration that defies easy explanation through known geological processes. Such extreme elongation raises questions about the object's structural integrity and formation history. Natural bodies with aspect ratios exceeding about 3:1 typically prove unstable under their own rotation, with centrifugal forces eventually overcoming the weak gravitational self-attraction that holds small objects together. The fact that Oumuamua has maintained its elongated form despite millions of years of tumbling motion suggests either unusually strong internal cohesion or rotational periods slow enough to avoid disruptive forces. The rotation period itself presents another puzzle wrapped within the broader mystery of the object's behavior. 7 hours and 18 minutes represents a relatively slow spin compared to many asteroids, which often rotate several times per hour due to the cumulative effects of thermal forces and small collisions over geological time. This measured cadence suggests internal structure capable of maintaining coherence against the gentle but persistent forces that tend to spin up small objects through thermally driven torques. Astronomers studying the light curve data notice subtle asymmetries that hint at an irregular surface covered with features that reflect light differently depending on viewing angle. Perhaps ancient impact craters dot the object's elongated form, or compositional variations create patches of higher and lower reflectivity across its tumbling surface. These brightness variations tell stories written in reflected photons, encoding information about surface geology that formed under alien suns in stellar systems whose planets followed different evolutionary paths than those in our cosmic neighborhood. The spectroscopic observations reveal a surface composition reminiscent of metallic asteroids found in the inner regions of our solar system, yet with subtle differences that speak of formation processes under different conditions. The reflected light carries the signatures of minerals that crystallized in environments with different temperatures, pressures, and chemical abundances than those that shape the rocky bodies orbiting our Sun. These compositional hints suggest origins in a planetary system where the distribution of elements followed patterns established by a different stellar formation history. As Oumuamua tumbles through space, its elongated form experiences gravitational forces that vary subtly with orientation relative to the Sun and planets. When the long axis aligns with the direction of solar gravity, the object experiences slightly different tidal forces than when it presents its narrow profile. These variations are minuscule by terrestrial standards, but over the course of months, they could theoretically contribute to the tiny accelerations that puzzle astronomers trying to predict the visitor's exact trajectory. The tumbling motion also affects how solar radiation pressure acts on the object's surface. As different faces rotate into and out of direct sunlight, the net force from reflected photons changes direction and magnitude in complex patterns tied to the rotation period. This coupling between spin and radiation pressure creates a three-dimensional dance of forces that complicates efforts to model the object's motion using conventional orbital mechanics software designed for more symmetrical bodies. Temperature variations across the rotating surface add another layer of complexity to the physics governing Oumuamua's behavior. The side facing the Sun heats to temperatures that could sublimate volatile compounds, while the shadowed hemisphere radiates heat into space and cools toward the cosmic background temperature of just a few degrees above absolute zero. This thermal cycling creates expansion and contraction stresses that could fracture surface materials or release trapped gases in patterns synchronized with the rotation period. Yet, despite intensive spectroscopic monitoring throughout the object's passage through the inner solar system, astronomers detected no evidence of outgassing that might explain the mysterious accelerations. No water vapor, carbon dioxide, or other common cometary volatiles appeared in the spectra, leaving researchers to wonder whether the object's composition differs fundamentally from that of solar system comets, or whether some more exotic mechanism drives the observed trajectory deviations. The rotation continues now in the darkness beyond Mars, where sunlight grows weak and the object fades toward invisibility against the stellar background. Each 7-hour cycle carries Oumuamua further from human observation, its tumbling form disappearing into the cosmic deep while still maintaining the precise rotational rhythm that has marked its journey through interstellar space. The spin carries with it all the encoded information about the object's origins, structure, and composition data that will remain forever locked in the mathematics of its light curve, sleeping quietly in astronomical databases until future interstellar visitors arrive to either confirm or contradict the mystery of shapes that shouldn't exist in the orderly realm of gravitational mechanics. Gravity speaks in mathematics so elegant that Einstein called them the most beautiful equations he had ever encountered. Relationships between mass, energy, and the curvature of space-time that govern everything from falling apples to orbiting galaxies with unwavering consistency. For 3 centuries, these laws have predicted the motion of celestial objects with such precision that astronomers routinely calculate planetary positions decades in advance, timing eclipses to the second and guiding spacecraft across billions of miles to rendezvous with distant worlds. Yet now, in the quiet halls of observatories around the world, these same equations whisper uncertainties that make even the most confident theorists pause and reconsider their assumptions about how the universe actually works. The deviation appears first as a subtle discrepancy between predicted and observed positions, a difference measured in thousandths of degrees that would escape notice except for the extraordinary precision of modern astrometric measurements. When Marco Micheli and his colleagues at the European Space Agency analyzed months of tracking data for Oumuamua, they discovered that the object's actual trajectory deviates systematically from the path predicted by gravitational dynamics alone. The discrepancy accumulates slowly but persistently, like a clock that gains a few seconds each day until the error becomes impossible to ignore. In the language of orbital mechanics, Oumuamua experiences what astronomers term non-gravitational acceleration, forces that push the object in ways that cannot be explained by the Sun's gravitational field or the gravitational influence of planets and moons. The acceleration vector points roughly away from the Sun, suggesting some mechanism that operates more strongly when the object lies closer to our star and weakens as it travels toward the outer solar system. This radial pattern resembles the acceleration signatures observed in active comets, where sublimating ice creates jets of vapor that act like natural rocket engines. The magnitude of this mysterious acceleration measures approximately 5 millionths of a meter per second, squared a force so gentle that it would barely register on the most sensitive laboratory instruments, yet persistent enough to bend the trajectory of a million-ton object over the course of months. To put this force in perspective, it equals roughly the weight of a grain of sand pressing against a human hand, but applied continuously to an object the size of a mountain. This tiny push accumulates into trajectory changes measured in thousands of kilometers. Scientists working to understand this anomaly face the uncomfortable reality that none of the conventional explanations prove adequate to account for the observed acceleration. Solar radiation pressure, the gentle push of photons reflecting off the object's surface, could theoretically create forces in the right direction and with the proper dependence on solar distance. Yet when researchers calculate the radiation pressure that Oumuamua should experience based on its estimated size, mass, and surface properties, the predicted force falls short of the observations by factors that require increasingly exotic assumptions about the object's composition and structure. The Yarkovsky effect, which causes rotating objects to experience tiny propulsive forces when they absorb sunlight and re-radiate it as thermal infrared radiation, offers another potential mechanism for non-gravitational acceleration. This thermal rocket effect has been measured for near-Earth asteroids, where it causes orbital decay rates that accumulate over thousands of years into measurable changes in orbital periods. Yet the acceleration experienced by Oumuamua exceeds what the Yarkovsky effect could reasonably produce for an object of its presumed size and rotation rate by margins that stretch physical plausibility. Perhaps most puzzling is the complete absence of any observable outgassing that might explain the acceleration through conventional cometary mechanisms. Despite intensive spectroscopic monitoring throughout the object's passage through the inner solar system, astronomers detect no evidence of water vapor, carbon dioxide, methane, or any of the other volatile compounds that typically sublimate from comet nuclei when heated by solar radiation. The lack of a visible coma or dust tail further confirms that Oumuamua behaves unlike any comet previously studied, yet it experiences accelerations characteristic of active sublimation processes. Some researchers propose that the object might be outgassing materials too faint to detect with current instrumentation, perhaps hydrogen molecules that escape from water-rich subsurface layers without creating visible dust clouds. Hydrogen gas would be essentially invisible to optical telescopes and might escape detection in infrared spectra if the outgassing rates remained below instrumental sensitivity thresholds. This hypothesis requires that Oumuamua contains substantial quantities of water ice despite its asteroid-like surface composition, a combination that challenges conventional understanding of how different types of solar system bodies form and evolve. Alternative explanations venture into increasingly speculative territory, proposing that the object might consist of exotic materials with unusual optical or thermal properties that amplify radiation pressure effects beyond what conventional physics would predict. Some theoretical models suggest that Oumuamua could be a fragment of disrupted planetary material with internal structures that create preferential outgassing along specific axes, or perhaps an aggregation of smaller components held together by weak cohesive forces that allow thermal expansion to create net propulsive effects. The acceleration mystery deepens when researchers attempt to model the object's motion using the same sophisticated software packages that successfully predict the trajectories of comets, asteroids, and interplanetary spacecraft. These programs incorporate decades of accumulated knowledge about gravitational dynamics, radiation pressure, thermal effects, and outgassing phenomena, yet they consistently fail to reproduce Oumuamua's observed behavior without invoking physical parameters that seem implausibly extreme for a natural object. As the visitor continues its journey outward through the solar system, growing fainter with each passing week until it disappears beyond the reach of even the most powerful telescopes, it carries with it a fundamental challenge to humanity's understanding of celestial mechanics. The equations that have guided astronomical calculations for centuries now sleep uneasily, disturbed by observations that suggest the universe still holds surprises for those humble enough to admit that their mathematical models might be incomplete. Gravity continues to whisper its ancient truths about the curvature of space-time and the attraction between masses. But Oumuamua's trajectory speaks of forces that operate beyond the familiar boundaries of gravitational theory. Mysterious accelerations that push objects through space, according to rules that scientists have yet to decipher. The discrepancy between prediction and observation lingers in astronomical databases like an unsolved equation, waiting for future interstellar visitors to either confirm or contradict the growing suspicion that objects from other star systems follow different physical laws than those that govern the predictable motions of planets and comets born in our cosmic neighborhood. In the realm of cometary science, where astronomers study the pristine remnants of solar system formation, certain visual signatures mark the transition from inert rock to active sublimating body with unmistakable clarity. When comets approach the Sun and their surfaces warm beyond the threshold, temperatures where frozen volatiles transition directly from solid to gas, they develop the characteristic fuzzy appearance of a coma, a diffuse atmosphere of water vapor. Carbon dioxide, and organic compounds that escapes from the nucleus and expands into space. This outgassing process creates the spectacular tails that stretch millions of kilometers behind comets as they round the Sun, swept away by solar wind and radiation pressure into graceful curves that have inspired human imagination for millennia. Yet, Oumuamua passes through the inner solar system without displaying any of these telltale signs of cometary activity, maintaining the sharp, point-like appearance of an asteroid even as it experiences accelerations that should indicate vigorous outgassing. The most sensitive spectroscopic observations detect no trace of water vapor, carbon monoxide, methane, or ammonia escaping from its surface. Despite the fact that these compounds sublimate readily at temperatures the object surely experiences during its close approach to the Sun. The absence of detectable volatiles presents a profound puzzle for astronomers attempting to explain the mysterious forces that push the visitor away from purely gravitational trajectories. Spectroscopic analysis using the European Southern Observatory's Very Large Telescope and NASA's Hubble Space Telescope reveals surface composition reminiscent of metallic asteroids found in the inner regions of our solar system, with reflectance properties suggesting minerals rich in iron and nickel that formed under high-temperature conditions. These observations paint a picture of an object more similar to the differentiated fragments of ancient planetesimals than to the volatile rich bodies that populate the outer reaches of stellar systems. Yet, metallic surfaces should not produce the non-gravitational accelerations that characterize Oumuamua's trajectory, creating a contradiction between observed composition and observed dynamics that challenges fundamental assumptions about how different types of solar system bodies behave. The rotation period of 7.3 hours, measured through careful analysis of brightness variations as the elongated object tumbles through space, provides additional clues about its internal structure and cohesive strength. This relatively slow spin suggests that Oumuamua possesses sufficient structural integrity to maintain its elongated form despite the centrifugal forces that would tend to tear apart loosely aggregated rubble piles rotating at such rates. The stable rotation implies either unusually strong internal bonding or a monolithic structure carved from a single large body. Yet neither scenario easily explains how such an object could generate the subtle but persistent accelerations that alter its trajectory. Temperature models based on the object's distance from the Sun and estimated thermal properties suggest that surface temperatures during closest approach would have exceeded 300 Kelvin, warm enough to sublimate water ice, and many other common cometary volatiles at rates that should produce easily detectable outgassing. The thermal gradients between the sunlit and shadowed hemispheres of the tumbling object would create expansion and contraction stresses that could fracture surface materials and release trapped gases. Yet no such outgassing signature appears in the observational data despite intensive monitoring throughout the object's passage through the inner solar system. Some researchers propose that Oumuamua might be outgassing hydrogen molecules produced by the radiolysis of subsurface water ice, a process where high-energy cosmic ray particles break apart water molecules and create hydrogen gas that could escape through microscopic fractures in the surface. Hydrogen outgassing would be essentially invisible to optical and infrared telescopes, potentially explaining both the absence of detectable cometary activity and the presence of accelerations that push the object away from the Sun. This hypothesis requires that the visitor contains substantial quantities of buried water ice despite its asteroid-like surface appearance, a compositional profile that challenges conventional understanding of planetary formation processes. The hydrogen outgassing model faces its own theoretical difficulties, particularly in explaining how sufficient quantities of molecular hydrogen could escape from a presumably dense, rocky object without creating other observable effects. The process would require that cosmic ray bombardment over millions of years has gradually converted subsurface water ice into hydrogen gas that migrates through fracture networks to reach the surface. Yet the rates of hydrogen production and escape needed to explain the observed accelerations approach the limits of what seems physically reasonable for an object of Oumuamua's estimated size and composition. Alternative explanations venture into even more speculative territory, proposing that the object might represent a fragment of exotic material with unusual physical properties that amplify radiation pressure effects beyond what conventional physics would predict. Some theoretical models suggest that Oumuamua could be a highly porous aggregate with internal voids that create complex thermal dynamics, or perhaps a remnant of disrupted planetary material with layered structures that respond to solar heating in unexpected ways. The possibility that the visitor consists of materials formed under different stellar conditions than those that shaped objects in our solar system opens fascinating questions about planetary formation processes around other stars. The chemical composition and isotopic ratios locked within Oumuamua's crystalline structure encode information about stellar nucleosynthesis, planetary accretion, and surface evolution processes that operated in an alien stellar environment. Yet these secrets remain hidden beneath the mystery of why the object accelerates without visible outgassing. As weeks pass and Oumuamua fades beyond the sensitivity limits of even the most powerful telescopes, it carries away the answers to questions that have puzzled astronomers since its discovery. The object continues its silent journey through the outer solar system, still accelerating gently away from the Sun according to some mechanism that remains hidden from human understanding. No coma of escaping gases marks its passage. No tail of sublimated materials streams behind it. Yet, something invisible continues to push this ancient wanderer toward the darkness between stars, leaving behind only questions that sleep quietly in astronomical databases, waiting for future interstellar visitors to either confirm or contradict the puzzle of accelerations without observable cause. The silence of Oumuamua's passage speaks as loudly as any cometary display, suggesting that the universe contains types of objects that operate according to physical principles not yet incorporated into humanity's understanding of how matter behaves in the vacuum of space. The absence of expected signatures becomes itself a signature of something fundamentally different about this messenger from another star system. A reminder that the cosmos still holds surprises for those patient enough to observe and humble enough to admit when their theoretical models fail to explain what their instruments detect. In the quiet laboratories where theoretical physicists wrestle with the mysteries of interstellar visitors, a new hypothesis emerges from the intersection of solid-state physics and cosmic ray bombardment, proposing that invisible clouds of hydrogen molecules might explain the enigmatic accelerations that push Oumuamua away from purely gravitational trajectories. This elegant solution draws upon decades of research into how high-energy particles interact with water-rich materials in the vacuum of space, creating a cascade of chemical reactions that could generate the gentle but persistent forces observed in the object's anomalous motion. The theoretical foundation rests on the well-established phenomenon of radiolysis, where cosmic ray protons and alpha particles bombard water ice and break apart the molecular bonds that hold H2O together, creating free hydrogen atoms that can recombine into molecular hydrogen gas. Over millions of years of interstellar travel, this process could gradually convert subsurface water reservoirs into vast quantities of trapped hydrogen that migrate through microscopic fracture networks toward the surface. When solar heating raises surface temperatures above critical thresholds, this accumulated hydrogen escapes into space, creating a nearly invisible form of outgassing that produces accelerations without the dramatic visual signatures associated with conventional cometary activity. Darrell Seligman of Cornell University and Gregory Laughlin of Yale University developed mathematical models that quantify how much hydrogen Oumuamua would need to produce in order to account for the observed accelerations, calculating that the process requires outgassing rates of approximately 10 to the 16th molecules per second, a prodigious quantity that nonetheless remains below the detection limits of current spectroscopic instruments. Hydrogen molecules absorb and emit light at wavelengths that lie outside the sensitive ranges of most astronomical spectrographs, making this form of outgassing essentially invisible to the optical and infrared telescopes that monitored the object throughout its passage through the inner solar system. The hydrogen hypothesis faces immediate scrutiny from astronomers who question whether natural objects can store sufficient quantities of molecular hydrogen to sustain the required outgassing rates over the months-long observation period. Hydrogen represents the lightest and most volatile element in the periodic table, with thermal velocities at room temperature that exceed the escape velocities of small asteroids and comets by large margins. Retaining significant hydrogen reservoirs requires either extremely cold storage temperatures or physical trapping mechanisms that prevent the gas from escaping during the long journey through interstellar space. Theoretical calculations suggest that hydrogen could accumulate within Oumuamua's interior if the object maintained temperatures below approximately 50 Kelvin throughout its interstellar journey, conditions that exist in the deep space environment far from stellar heating sources. The gradual production of hydrogen through cosmic ray radiolysis would create internal gas pressures that could fracture surface materials and create pathways for eventual outgassing when solar heating raises temperatures above the retention threshold. This scenario requires that the object possess sufficient structural integrity to contain pressurized hydrogen while maintaining the elongated shape suggested by its dramatic brightness variations. Alternative versions of the hydrogen hypothesis propose that molecular hydrogen forms through different chemical pathways that might operate more efficiently under the specific conditions of interstellar travel. Solar wind particles and galactic cosmic rays carry energies that can drive complex organic chemistry in the surface layers of primitive objects, potentially creating hydrogen-rich compounds that decompose when heated by solar radiation. These surface chemistry models require less hydrogen storage capacity, but invoke reaction mechanisms that remain poorly understood for objects with the presumed composition and thermal history of interstellar visitors. The hydrogen outgassing model makes specific predictions about how the acceleration should vary with distance from the Sun, since the outgassing rate depends on surface temperature, which in turn depends on the intensity of solar heating. Observations of Oumuamua's trajectory show accelerations that peak during closest approach to the Sun and diminish as the object travels toward the outer solar system, a pattern consistent with thermally driven outgassing processes. Yet the precise functional relationship between solar distance and acceleration remains difficult to match using realistic models of hydrogen escape from rocky surfaces. Laboratory experiments designed to test the hydrogen hypothesis face significant technical challenges in reproducing the extreme conditions of interstellar space, where temperatures approach absolute zero and cosmic ray bombardment continues for millions of years without interruption. Researchers attempt to simulate these conditions using specialized vacuum chambers and particle accelerators, bombarding water-rich samples with high-energy protons while monitoring the production and retention of molecular hydrogen. These experiments provide valuable insights into the physics of radiolysis, but the timescales involved in natural hydrogen accumulation far exceed what laboratory studies can practically investigate. Spectroscopic searches for hydrogen outgassing from Oumuamua push the limits of observational astronomy, requiring specialized instruments sensitive to the ultraviolet wavelengths where hydrogen molecules absorb and emit light most strongly. The Hubble Space Telescope conducts targeted observations searching for hydrogen Lyman alpha emission that might reveal ongoing outgassing. But the measurements remain inconclusive due to the faintness of the expected signals and interference from interplanetary hydrogen that pervades the solar system. The absence of detectable hydrogen signatures could indicate either that outgassing rates remain below instrumental thresholds or that the hydrogen hypothesis itself requires modification. Independent theoretical analyses examine whether objects with Oumuamua's estimated mass and size could realistically contain the hydrogen reservoirs needed to sustain the observed accelerations without undergoing catastrophic structural changes. The internal gas pressures required to store sufficient hydrogen approach levels that could fracture solid rock, raising questions about how the object maintains its structural integrity while serving as a pressurized hydrogen reservoir. These mechanical constraints suggest that any viable hydrogen outgassing model must incorporate sophisticated assumptions about the object's internal structure and material properties. As Oumuamua continues its journey beyond the reach of detailed observational study, the hydrogen hypothesis remains one of several competing explanations for its anomalous behavior, each with its own strengths and weaknesses in accounting for the observed trajectory deviations. The invisible nature of hydrogen outgassing means that this explanation may never be definitively confirmed or refuted based on observations of the original object, leaving astronomers to await future interstellar visitors that might provide additional tests of the theoretical models developed to explain the mystery of accelerations without visible cause. The hydrogen hypothesis sleeps quietly in the scientific literature, an elegant solution to a cosmic puzzle that may represent humanity's first glimpse into the exotic physics of objects formed around other stars, where different stellar environments create materials with properties that challenge earthbound intuitions about how matter behaves in the vacuum of space. In the realm where photons carry momentum through the vacuum of space, even the gentle pressure of starlight becomes a force capable of altering the trajectories of objects that drift through the cosmic void. Solar radiation pressure operates according to principles so subtle that they escaped scientific attention until the late 19th century, yet so fundamental that modern spacecraft designers routinely incorporate these forces into mission planning for interplanetary voyages that unfold over years or decades. Each photon that strikes a surface and reflects back into space transfers a tiny quantity of momentum to the reflecting object, creating accelerations measured in fractions of millimeters per second squared that accumulate over time into measurable changes in orbital dynamics. For Oumuamua, tumbling through the inner solar system with its elongated form alternately presenting broad and narrow profiles to the sun's radiant output. Radiation pressure effects should vary in complex patterns tied to the object's rotation period and orientation relative to our star. When the long axis aligns perpendicular to the direction of solar radiation, the cross-sectional area exposed to photon bombardment reaches its maximum, creating the strongest radiation pressure forces. As rotation carries the narrow end into solar alignment, the effective area diminishes dramatically, reducing the pressure to levels that might barely register in precise astrometric measurements. Theoretical calculations of radiation pressure, acceleration, depend critically on assumptions about the object's size, mass, surface reflectivity, and geometric shape parameters that remain poorly constrained despite intensive observational efforts throughout Oumuamua's passage through the inner solar system. The dramatic brightness variations that reveal the object's elongated form also complicate efforts to determine its true dimensions. Since the observed light curve depends on viewing geometry as well as physical characteristics, estimates of the object's length range from 200 to 800 meters, with corresponding uncertainties in mass that span more than an order of magnitude. Surface reflectivity measurements, derived from the quantity of sunlight that Oumuamua reflects compared to the amount it receives, suggest values typical of carbonaceous asteroids or primitive cometary nuclei materials that absorb most incident radiation and reflect only a small fraction back into space. Low reflectivity implies that radiation pressure effects should be correspondingly weak, since the momentum transfer from absorbed photons tends to be less efficient than the transfer from reflected photons. Yet the object's actual surface composition might differ significantly from solar system materials, potentially exhibiting optical properties that enhance radiation pressure beyond what conventional models predict. The orientation and rotation of Oumuamua introduce additional complexities into radiation pressure calculations, since the net force depends on how reflected photons distribute their momentum across the object's tumbling surface. If the elongated form maintains a stable rotation axis aligned with its long dimension, radiation pressure would create systematic torques that could gradually alter the spin rate over timescales comparable to the orbital observation period. These spin-orbit coupling effects have been observed in near-Earth asteroids, where radiation pressure gradually changes rotation periods in ways that can be measured through careful monitoring of brightness variations. Abraham Loeb of Harvard University proposes that Oumuamua might represent an artificially constructed object with geometric and optical properties specifically designed to maximize radiation pressure acceleration, suggesting that the visitor could be a defunct solar sail from an extinct technological civilization. This hypothesis requires that the object possess an extremely low mass-to-area ratio, essentially behaving like a thin sheet of reflective material tumbling through space. While such geometric characteristics could theoretically explain the observed accelerations through conventional radiation pressure physics, they require structural properties unlike any natural object previously studied in our solar system. Alternative radiation pressure models explore whether Oumuamua's surface might exhibit unusual optical characteristics that enhance photon momentum transfer beyond what conventional materials would produce. Theoretical studies examine surfaces with microscopic textures that could trap and re-radiate photons in preferential directions, creating net forces larger than those predicted by simple reflection models. These enhanced radiation pressure scenarios require surface structures with periodicities comparable to visible light wavelengths, patterns that might arise through natural processes operating under different environmental conditions than those found in our solar system. The temperature-dependent nature of radiation pressure adds another layer of complexity to theoretical models. Since surface heating by solar radiation affects both the efficiency of photon reflection and the thermal emission characteristics that contribute to overall momentum transfer. As Oumuamua approaches perihelion and surface temperatures rise, thermal emission of infrared photons could create additional propulsive forces that supplement direct radiation pressure effects. The magnitude and direction of these thermal forces depend on surface material properties and temperature gradients that remain poorly constrained by observational data. Detailed numerical simulations attempt to model the combined effects of solar radiation pressure, thermal emission, and rotational dynamics for objects with Oumuamua's observed characteristics. Yet these calculations consistently fall short of explaining the magnitude of acceleration observed in trajectory analyses. Even under the most optimistic assumptions about surface reflectivity, geometric shape, and thermal properties, radiation pressure forces remain insufficient to account for the trajectory deviations by factors of 3 to 10. This shortfall suggests either that conventional radiation pressure models incompletely describe the physics of photon momentum transfer, or that additional forces contribute to the object's anomalous acceleration. The discrepancy between theoretical predictions and observational results highlights fundamental limitations in humanity's understanding of how exotic objects behave under the influence of stellar radiation. Oumuamua's presumed origins in a different stellar environment raise possibilities that its material properties reflect formation processes that operated under different conditions than those that shaped objects in our solar system. Surface compositions, crystal structures, and microscopic textures formed around other stars might exhibit optical characteristics that amplify radiation pressure effects in ways not anticipated by theoretical models based on terrestrial and solar system analogs. As Oumuamua continues its journey outward through regions where solar radiation pressure diminishes with the square of distance from the Sun, the object carries with it questions about the fundamental physics of light-matter interaction in astronomical contexts. The gentle push of photons continues to operate according to the principles of conservation of momentum and energy. Yet the magnitude of these effects apparently exceeds what conventional models predict for natural objects, suggesting that the universe contains materials and structures that challenge earthbound assumptions about how radiation pressure influences the motion of matter through space. The silent pressure of starlight accompanies Oumuamua toward the darkness between stars, a force so subtle it barely registers in human experience, yet persistent enough to alter the trajectories of mountain-sized objects over the course of months. This cosmic reminder that even the gentlest forces accumulate into significant effects over astronomical timescales sleeps quietly in the equations that govern orbital mechanics, waiting for future interstellar visitors to either confirm or contradict the growing suspicion that objects from other stellar systems follow different physical laws than those that govern the predictable motions of planets and comets born in our cosmic neighborhood. 2 years after Oumuamua's puzzling departure from the solar system, another interstellar visitor announces its arrival with characteristics that restore astronomers' confidence in their understanding of how objects from other star systems should behave when they wander through our cosmic neighborhood. On August 30th, 2019, Gennady Borisov, an amateur astronomer working with a 0.65-meter telescope at his private observatory in Crimea, discovers a comet-like object following a hyperbolic trajectory that marks it unmistakably as the second confirmed interstellar interloper to visit our solar system within recorded human history. The new visitor, designated 2I Borisov in honor of its discoverer, displays all the conventional signatures that were mysteriously absent from Oumuamua's passage through the inner solar system. As it approaches perihelion, solar heating begins sublimating volatile compounds from its nucleus, creating a diffuse coma of water vapor and dust that expands around the central body like a gossamer atmosphere. Spectroscopic observations reveal the familiar molecular signatures of cometary outgassing water, carbon monoxide, and cyanogen escaping from the nucleus at rates that increase predictably as the comet draws closer to the Sun. Unlike its enigmatic predecessor, 2I Borisov behaves exactly as theoretical models predict an interstellar comet should behave, following orbital dynamics that can be precisely calculated using conventional gravitational mechanics supplemented by well-understood outgassing forces. The non-gravitational accelerations produced by sublimating ice create jets of vapor that act like natural rocket engines, pushing the comet slightly away from its purely gravitational trajectory in ways that match decades of accumulated knowledge about how active comets move through space. The contrast between the two interstellar visitors could hardly be more stark, highlighting the profound mystery that Oumuamua represents in the context of comparative planetology and solar system dynamics. Where 2I Borisov displays a visible coma and develops a modest tail as it rounds the Sun, Oumuamua remained point-like throughout its passage, showing no detectable signs of volatile sublimation despite experiencing similar solar heating, where 2I Borisov's acceleration can be explained through conventional outgassing models. Oumuamua's trajectory deviations require exotic hypotheses that stretch the boundaries of established physics. Detailed observations of 2I Borisov using the Hubble Space Telescope and ground-based facilities around the world reveal a nucleus perhaps 1 to 4 kilometers in diameter, significantly larger than estimates for Oumuamua, but within the size range typical of solar system comets. The rotation period of approximately 25 hours suggests a more spherical or potato-shaped object rather than the extremely elongated form inferred for the first interstellar visitor. These conventional characteristics make 2I Borisov easier to study and understand using existing theoretical frameworks developed through decades of cometary science. Spectroscopic analysis of the outgassing reveals compositional similarities to solar system comets, with water vapor dominating the sublimation products supplemented by carbon monoxide, methane, and various organic compounds. The ratios of different molecular species match those observed in comets from the Oort cloud, suggesting that planetary formation processes around other stars produce volatile-rich objects with chemical compositions remarkably similar to those found in our own stellar system. This compositional concordance implies that the basic physics and chemistry of planetary accretion operate according to universal principles that transcend individual stellar environments. Yet, subtle differences in isotopic ratios and trace molecular abundances hint at formation conditions that differed from those in our solar system, encoding information about stellar nucleosynthesis, disk chemistry, and thermal processing in an alien planetary environment. The carbon monoxide abundance in 2I Borisov's coma appears enhanced relative to water compared to typical solar system comets, suggesting formation in a stellar disk with different temperature gradients or chemical evolution pathways. These compositional variations represent humanity's first direct samples of materials from another star system, even though the samples exist only as gas molecules escaping into space. The predictable behavior of 2I Borisov allows astronomers to calculate its orbital history with confidence, tracing its trajectory backward through interstellar space to estimate its stellar origins. Unlike Oumuamua, whose anomalous accelerations complicate efforts to determine its precise interstellar velocity and direction of arrival, 2I Borisov follows a well-defined hyperbolic orbit that can be extrapolated using conventional celestial mechanics. These calculations suggest the comet originated from the direction of the constellation Cassiopeia, approaching our solar system at a relative velocity of approximately 32 kilometers per second. The successful prediction of 2I Borisov's behavior using established cometary physics validates theoretical models that failed so dramatically to explain Oumuamua's characteristics, suggesting that the first interstellar visitor represents a genuine anomaly rather than a fundamental failure of astronomical understanding. This validation provides confidence that conventional physics remains adequate to describe most interstellar objects, while highlighting the exceptional nature of whatever mechanism drove Oumuamua's mysterious accelerations. Comparative studies of the two interstellar visitors reveal the diversity that characterizes objects formed around different stars under varying environmental conditions. Where 2I Borisov represents a relatively conventional comet that happens to originate from another stellar system, Oumuamua appears to belong to a category of objects with no known analogues in our solar system, either highly evolved comets that have lost their volatile content through prolonged heating, exotic rocky bodies with unusual structural properties, or perhaps fragments of disrupted planetary material with compositions and characteristics that reflect formation processes not represented among local objects. The familiar face of 2I Borisov provides a comforting contrast to the alien strangeness of Oumuamua, demonstrating that interstellar space contains objects that behave according to familiar physical principles alongside others that challenge humanity's understanding of how matter moves through the cosmic void. As 2I Borisov continues its own journey past perihelion and begins the long voyage back toward interstellar space, it carries with it the reassurance that some cosmic mysteries yield to conventional explanation, while others, like the enigmatic accelerations that pushed Oumuamua away from purely gravitational trajectories, remain wrapped in theoretical uncertainties that sleep quietly in astronomical databases, waiting for future visitors to either confirm or contradict the growing catalogue of interstellar anomalies that challenge earthbound assumptions about universal physical laws. The two messengers from distant stars continue their separate journeys into the cosmic deep, one carrying answers that validate human understanding of cometary physics, the other bearing questions that may require entirely new theoretical frameworks to resolve, both serving as reminders that the universe contains wonders that transcend the comfortable boundaries of established science. In the automated detection systems that scan the night sky for moving objects, another anomalous trajectory emerges from the background noise of routine astronomical observations, carrying with it the promise of further insights into the mysterious physics that govern interstellar visitors to our solar system. The Asteroid Terrestrial Impact Last Alert System, known by its acronym ATLAS, operates a network of robotic telescopes designed to identify potentially hazardous asteroids that might threaten Earth. Yet on this occasion, the survey captures something far more exotic, a third candidate for interstellar origin that exhibits orbital characteristics even more perplexing than those that puzzled astronomers studying Oumuamua's anomalous accelerations. The object, provisionally designated 3I Atlas pending confirmation of its interstellar status, follows a trajectory that appears hyperbolic when analyzed using conventional orbital determination software, suggesting origins beyond the gravitational boundary of our solar system. Yet, unlike the clear-cut hyperbolic orbits of Oumuamua and 2I Borisov, this new visitor's trajectory exhibits subtle characteristics that challenge the binary classification system that distinguishes between bound and unbound orbits, creating ambiguities that reflect either measurement uncertainties or genuinely unusual orbital dynamics. Initial observations suggest an object perhaps 300 meters in diameter tumbling through space with a rotation period that appears to vary over timescales of days to weeks, implying either a complex internal structure that allows different components to rotate at different rates, or external forces that systematically alter the object's angular momentum through mechanisms that remain poorly understood. The brightness variations associated with this irregular rotation create light curves unlike any previously observed for asteroids or comets, patterns that suggest either highly asymmetric geometry or surface features that reflect light with unusual efficiency variations across different viewing angles. Spectroscopic analysis reveals surface composition that appears intermediate between the metallic characteristics inferred for Oumuamua and the volatile-rich materials that characterize typical comets, suggesting either a mixed composition that reflects multiple formation episodes or a single formation process that operated under conditions not represented in our solar system. The spectral signatures include absorption features that correspond to both rocky silicate minerals and organic compounds, yet the relative abundances and molecular structures differ subtly from those observed in solar system objects, encoding information about stellar nucleosynthesis and planetary formation processes that operated in an alien stellar environment. The trajectory analysis that initially suggested interstellar origins becomes increasingly complicated as observational precision improves and the dataset expands to cover longer time baselines. Robert Varick, the same astronomer who discovered Oumuamua, leads the team analyzing 3I Atlas's orbital characteristics and discovers that the object's motion cannot be adequately described using conventional gravitational dynamics, even when supplemented by the radiation pressure and outgassing models that successfully explain the behavior of most asteroids and comets. Like Oumuamua before it, 3I Atlas appears to experience non-gravitational accelerations that push it away from purely Keplerian trajectories in ways that conventional physics struggles to explain. Yet the magnitude and direction of these forces differ significantly from those observed for the first interstellar visitor, suggesting either different physical mechanisms or objects with fundamentally different structural and compositional characteristics. The accelerations appear to vary with both solar distance and object orientation in patterns that resist straightforward interpretation using existing theoretical frameworks. Temperature modeling based on the object's distance from the Sun and estimated thermal properties suggests surface conditions that should trigger outgassing of volatile compounds if the object contains significant quantities of ice or other sublimable materials. Yet, spectroscopic monitoring reveals no clear evidence of cometary activity, no water vapor, carbon dioxide, or other common volatiles escaping from the nucleus despite surface temperatures that exceed the sublimation points of most compounds that freeze under interstellar conditions. This absence of detectable outgassing recreates the same puzzle that characterized Oumuamua's passage through the inner solar system. The lack of observable cometary activity combined with measurable non-gravitational accelerations suggests either that both interstellar visitors employ similar exotic mechanisms to generate propulsive forces, or that objects from other star systems possess physical characteristics that differ fundamentally from those of solar system bodies. The convergence of anomalous behavior across multiple interstellar objects implies systematic rather than coincidental departures from conventional physics, hinting at universal processes that operate beyond the boundaries of current astronomical understanding. Orbital integration studies attempt to trace 3I Atlas's trajectory backward through time to estimate its interstellar velocity and direction of approach. Yet the non-gravitational forces that affect its current motion also influenced its past trajectory in ways that introduce large uncertainties into historical reconstructions. Unlike 2I Borisov, whose well-understood cometary behavior allows precise calculation of its stellar origins, 3I Atlas carries its secrets locked within the same mysterious accelerations that prevent astronomers from definitively determining whether it truly originated beyond our solar system or represents an unusual solar system object with exotic dynamical characteristics. The ambiguity surrounding 3I Atlas's classification reflects broader challenges in distinguishing between interstellar visitors and highly eccentric solar system objects that venture far from the Sun before returning on extremely long-period orbits. Some Oort cloud comets follow trajectories so elongated that they appear nearly parabolic, creating observational signatures that can be difficult to distinguish from genuinely hyperbolic interstellar orbits without extensive data covering multiple years of observation. The non-gravitational forces that characterize both Oumuamua and 3I Atlas introduce additional complications that blur the boundaries between different categories of solar system objects. Statistical analyses of the rate at which interstellar objects pass through the inner solar system suggest that humanity should expect to discover 1 or 2 such visitors per year using current survey capabilities, implying that Oumuamua, 2I Borisov, and 3I Atlas represent the first members of a previously hidden population of cosmic wanderers that drift between star systems carrying information about planetary formation processes throughout the galaxy. Yet, if a significant fraction of these objects exhibit the anomalous acceleration characteristics observed in the first and third visitors, astronomers face the prospect of confronting fundamental gaps in their understanding of how matter behaves under the exotic conditions of interstellar space. As 3I Atlas continues its journey through the outer solar system, growing fainter with each passing week as it travels beyond the reach of detailed spectroscopic study, it carries with it the same unanswered questions that accompanied Oumuamua into the cosmic deep. The mysterious accelerations that push both objects away from purely gravitational trajectories remain unexplained despite intensive theoretical investigation, suggesting that the universe operates according to physical principles that transcend the comfortable boundaries of earthbound experience. Principles that sleep quietly in the equations of celestial mechanics, waiting for future discoveries to either validate or revolutionize humanity's understanding of how objects move through the vast emptiness between stars. In the orbital mechanics laboratories, where celestial dynamicists solve the differential equations that govern planetary motion, computer simulations struggle to reproduce the trajectories of interstellar visitors with the precision that characterizes predictions for conventional solar system objects. The elegant mathematical frameworks that successfully guide spacecraft to distant planets and predict the return of periodic comets with clockwork accuracy encounter systematic failures when applied to objects that originate beyond the gravitational boundary of our star system, suggesting fundamental gaps in humanity's understanding of how exotic materials behave under the influence of stellar radiation and gravitational fields. Multiple objects now challenge the comfortable predictability of Newtonian mechanics, each carrying its own signature of anomalous accelerations that resist explanation through conventional physics. Oumuamua pioneered this category of cosmic puzzles with its mysterious non-gravitational forces that pushed it away from purely gravitational trajectories, despite the absence of detectable outgassing. 2I Borisov provided a reassuring counterexample, behaving exactly as theoretical models predict for volatile-rich comets, yet its conventional characteristics only emphasize the profound strangeness of its predecessor and successor. Now, 3I Atlas joins the growing catalog of interstellar anomalies, exhibiting trajectory deviations that differ in both magnitude and direction from those observed for Oumuamua, while sharing the common characteristic of accelerations that cannot be explained using established models of radiation pressure, thermal effects, or cometary outgassing. The convergence of unexplained behavior across multiple visitors suggests systematic rather than coincidental departures from expected orbital dynamics, implying either that interstellar objects possess physical properties unlike any materials found in our solar system, or that fundamental aspects of celestial mechanics remain incompletely understood. The statistical likelihood of discovering multiple anomalous objects within the span of a few years, given the rarity of interstellar visitors and the brief history of systematic sky surveys capable of detecting them, raises questions about whether anomalous accelerations represent the norm rather than the exception for objects that drift between star systems. If most interstellar visitors exhibit non-gravitational forces that conventional physics cannot explain, astronomers face the uncomfortable prospect that their theoretical frameworks fail to describe a significant category of cosmic phenomena, leaving gaps in understanding that span the entire field of orbital mechanics. Comparative analysis of the 3 confirmed interstellar visitors reveals patterns that hint at underlying physical principles while refusing to yield definitive explanations for the observed anomalies. All 3 objects approach the solar system from different directions in interstellar space, suggesting diverse stellar origins rather than a common source region that might explain shared characteristics through similar formation or evolutionary processes. Yet, Oumuamua and 3I Atlas both exhibit mysterious accelerations in the absence of detectable outgassing, while 2I Borisov displays conventional cometary behavior that conforms to established theoretical expectations. The size distribution of interstellar objects appears to favor smaller bodies similar to Oumuamua and 3I Atlas over larger comets like 2I Borisov, suggesting either observational selection effects that make smaller objects easier to detect when they exhibit anomalous brightening, or genuine physical processes that preferentially eject smaller fragments from stellar systems during planetary formation or evolution. The predominance of sub-kilometer objects among confirmed interstellar visitors implies that most cosmic wanderers represent debris from catastrophic events rather than intact planetary bodies. Yet this interpretation struggles to explain why such fragments should exhibit the structural coherence necessary to survive millions of years of interstellar travel. Orbital eccentricity measurements reveal that interstellar visitors approach the solar system with a wide range of velocities and trajectory geometries, from nearly parabolic orbits that barely exceed escape velocity to highly hyperbolic paths that suggest ejection from stellar systems at speeds far exceeding typical planetary formation scenarios. This velocity distribution encodes information about the dynamical processes that liberate objects from their parent star systems, yet the mechanisms responsible for accelerating material to such high speeds remain poorly understood and may require gravitational interactions with massive planets or stellar companions operating over timescales that span millions of years. The absence of clear correlations between object size, composition, trajectory geometry, and anomalous acceleration characteristics frustrates efforts to develop unified theoretical explanations for interstellar visitor behavior. Each object appears to represent a unique combination of physical properties that defies simple categorization, suggesting either extraordinary diversity among planetary formation processes throughout the galaxy or systematic measurement uncertainties that obscure underlying patterns in the observational data. The lack of obvious trends implies that understanding interstellar objects may require theoretical frameworks that accommodate greater complexity than those developed for solar system bodies. Dynamical modeling efforts attempt to trace the galactic orbits of interstellar visitors backward through time to identify their stellar origins. Yet the same non-gravitational forces that complicate solar system trajectory predictions also introduce large uncertainties into historical reconstructions that span millions of years of galactic evolution. The inability to precisely determine where these objects originated limits astronomers' ability to understand the stellar and planetary environments that shaped their formation, leaving fundamental questions about interstellar object populations unanswered despite intensive observational and theoretical investigation. The growing database of interstellar visitor observations reveals temporal patterns that suggest seasonal variations in discovery rates, possibly reflecting either observational biases associated with Earth's orbital motion around the Sun, or genuine clustering in the directions from which interstellar objects approach our stellar system. These patterns hint at large-scale galactic dynamics that influence the distribution of cosmic wanderers throughout local space. Yet the short observational baseline and small sample size preclude definitive conclusions about the galactic environment through which our solar system travels. Computer simulations designed to model the long-term evolution of interstellar object populations throughout the Milky Way suggest that most cosmic wanderers originate from gravitational interactions that occur during the early phases of planetary system formation. When massive planets migrate through stellar disks and eject smaller bodies into interstellar space through close encounters that accelerate them beyond escape velocity. Yet, these formation scenarios predict populations dominated by volatile-rich comets, rather than the rocky or metallic objects that characterize most confirmed interstellar visitors, suggesting either that observational selection affects biased discoveries toward unusual objects, or that the theoretical models incompletely represent the diversity of planetary formation outcomes. The dance of unlikely orbits continues throughout the outer solar system, where multiple interstellar visitors follow trajectories that curve through space according to gravitational laws supplemented by mysterious forces that operate beyond the boundaries of established physics. Each object carries encoded information about stellar environments and planetary formation processes that operated billions of years ago in stellar systems, whose planets evolved along pathways different from those that shaped our cosmic neighborhood. Yet, the secrets remain locked within the mathematics of anomalous accelerations that refuse to yield to conventional theoretical analysis, sleeping quietly in orbital databases while awaiting future discoveries that may finally illuminate the exotic physics that governs the motion of matter through the vast emptiness between stars. Within the crystalline lattices that comprise the solid matrix of interstellar wanderers, isotopic signatures tell stories written in the nuclear furnaces of stars that burned and died before our sun condensed from the primordial gas clouds of stellar formation. These atomic fingerprints encode information about stellar nucleosynthesis processes that operated under different conditions than those that forged the elements found in our solar system, creating subtle variations in the ratios of carbon-12 to carbon-13, oxygen-16 to oxygen-18, and dozens of other isotopic pairs that serve as chemical fossils, preserving the history of galactic evolution across billions of years of cosmic time. Each interstellar visitor carries within its molecular structure a library of data about the stellar environment where its constituent atoms originally formed, information that spans the entire periodic table from hydrogen forged in the Big Bang to heavy elements created in the explosive deaths of massive stars. The relative abundances of different isotopes reflect the mass and metallicity of the parent star, the duration and intensity of nuclear burning phases, and the mechanisms by which newly synthesized elements mixed with the interstellar medium to become incorporated into subsequent generations of planetary formation processes. Spectroscopic analysis of the gas clouds that escape from active comets like 2I Borisov provides humanity's first direct measurements of isotopic ratios in materials formed around other stars, revealing compositions that differ subtly but measurably from those found in solar system objects. The carbon monoxide molecules that sublimate from the comet's nucleus carry isotopic signatures that suggest formation in a stellar disk with different chemical evolution pathways than those that operated during our solar system's formation, encoding information about stellar nucleosynthesis and galactic chemical evolution that extends humanity's understanding of cosmic chemistry beyond the local environment. The oxygen isotope ratios observed in 2I Borisov's outgassing products differ from those measured in solar system comets by margins that reflect either different stellar mass functions in the galactic neighborhood where the object formed, or temporal variations in galactic chemical evolution that operated over the hundreds of millions of years that separate different episodes of star formation. These isotopic variations provide direct evidence that planetary formation processes throughout the galaxy operate with raw materials that reflect diverse stellar environments and chemical evolution histories. For the rocky or metallic objects represented by Oumuamua and 3I Atlas, isotopic information remains locked within solid mineral phases that resist direct spectroscopic analysis using current observational techniques. The crystalline structures that form through high-temperature condensation processes in stellar disks around other stars preserve isotopic ratios that would reveal detailed information about stellar nucleosynthesis, planetary accretion, and thermal processing. Yet accessing this data requires either sample return missions that remain beyond current technological capabilities or future spectroscopic instruments with sensitivity far exceeding current observational limits. The elemental abundances inferred from surface reflectance spectra hint at formation environments with different temperature and pressure conditions than those that operated during terrestrial planet formation in our solar system. The apparent enhancement of metallic components relative to volatile compounds suggests either formation closer to the central star in systems with different radial temperature gradients, or subsequent evolutionary processes that preferentially removed lighter elements through mechanisms that remain poorly understood for objects that originate beyond our local stellar environment. Theoretical models of stellar nucleosynthesis predict systematic variations in isotopic ratios that depend on stellar mass, metallicity, and evolutionary phase, creating galactic scale patterns in the chemical composition of interstellar material that reflect the complex interplay between star formation, stellar death, and galactic dynamics. These models suggest that objects formed in different galactic environments should carry distinctive isotopic signatures that encode information about the stellar populations and chemical evolution pathways that operated in their formation regions. The age estimates for interstellar visitors span enormous ranges that reflect uncertainties in both their formation histories and the dynamical processes that ejected them from their parent stellar systems. Surface exposure dating. Using cosmic ray bombardment signatures suggests minimum ages measured in millions of years for the interstellar journey phase. Yet the original formation of these objects likely occurred billions of years ago during episodes of planetary accretion that may have preceded the formation of our solar system by substantial intervals. Mineral phases preserved within interstellar objects potentially include pre-solar grains that condensed directly from the atmospheres of evolved stars before being incorporated into planetary formation processes, creating a nested hierarchy of age scales that spans from the most recent surface modifications caused by cosmic ray bombardment to the oldest stellar nucleosynthesis processes that occurred in the early galaxy. These temporal layers encode information about galactic chemical evolution that extends far beyond the limited perspective available from studying only solar system materials. The crystalline structures formed under alien stellar conditions may exhibit polymorphic phases or mineral associations that differ from those found in terrestrial or meteoritic samples, reflecting pressure and temperature regimes that operated during planetary formation, processes around stars with different masses, compositions, or evolutionary histories. These exotic mineral phases could provide insights into planetary formation mechanisms that remain poorly understood even for our local stellar environment. Organic compounds detected in the spectra of interstellar visitors suggest chemical evolution pathways that operated in stellar disks with different volatile inventories and thermal structures than those that characterized the early solar nebula. The molecular complexity observed in interstellar space implies that prebiotic chemistry occurs throughout the galaxy under diverse environmental conditions, creating organic inventories that may differ significantly from those that contributed to the origin of life on Earth. Trace element signatures preserved in interstellar materials encode information about stellar nucleosynthesis processes that operated in different galactic environments, potentially including contributions from stellar populations with different initial mass functions, binary star evolution pathways, or supernova explosion mechanisms. These chemical fossils provide direct samples of stellar nucleosynthesis products that formed under conditions not represented in our local galactic neighborhood. As interstellar visitors continue their journeys toward the cosmic deep, they carry away these atomic libraries of galactic history, leaving behind only the brief spectroscopic glimpses that humanity has managed to capture during their fleeting passages through our solar system. The isotopic stories written in stellar furnaces billions of years ago continue to travel through interstellar space, encoded in crystalline matrices and molecular structures that preserve information about cosmic chemical evolution across timescales that span most of the history of the galaxy itself. These ancient starlight children drift through the darkness between stellar systems, each one a messenger carrying data about stellar nucleosynthesis, planetary formation, and chemical evolution from cosmic environments that may never be directly accessible to human observation. Their atomic signatures sleeping quietly within mineral lattices that formed under alien suns, waiting for future analytical techniques that might finally decode the complete chemical histories encoded within materials that originated in the stellar nurseries of distant galactic neighborhoods. In the computational laboratories, where astronomers wrestle with the fundamental equations that govern celestial mechanics, sophisticated orbital integration software encounters systematic failures when applied to the trajectories of interstellar visitors, producing residuals that accumulate over time into discrepancies measured in thousands of kilometers, despite starting from initial conditions determined with sub-arc-second precision. These mathematical breakdowns represent more than mere computational challenges. They signal fundamental gaps in humanity's understanding of how exotic objects behave under the influence of forces that operate beyond the comfortable boundaries of Newtonian gravitation and well-understood non-gravitational effects. The differential equations that describe orbital motion under gravitational forces alone possess elegant analytical solutions that have guided astronomical calculations for centuries, producing predictions of planetary positions, comet returns, and spacecraft trajectories with accuracies that approach the limits of observational precision. Yet, when these same mathematical frameworks encounter objects like Oumuamua and 3i Atlas, the solutions diverge from observational reality in ways that resist correction through conventional perturbation theory or improved numerical integration techniques. Marco Michele's team at the European Space Agency develops increasingly sophisticated orbital models that attempt to incorporate every known source of non-gravitational acceleration, from solar radiation pressure and thermal emission to relativistic effects and tidal forces from planetary encounters. Each refinement improves the theoretical predictions slightly, yet significant residuals persist that cannot be eliminated without invoking force models that require physical parameters far outside the range of reasonable estimates for natural objects with the presumed characteristics of interstellar visitors. The mathematical challenge deepens when researchers attempt to model the coupling between rotational dynamics and non-gravitational forces for objects with the extreme elongation inferred for Oumuamua and the irregular geometry suggested by 3i Atlas's variable light curve. The orientation-dependent nature of radiation pressure effects and thermal emission creates complex three-dimensional force patterns that vary with both solar distance and object attitude, producing orbital perturbations that require sophisticated numerical integration schemes to model accurately. Computational limitations impose practical constraints on the complexity of theoretical models that can be evaluated within reasonable timeframes using current computer resources. Full three-dimensional simulations that incorporate detailed surface thermal models, realistic radiation pressure calculations, and stochastic outgassing processes require computational resources that exceed what most research groups can access, forcing astronomers to rely on simplified approximations that may inadequately represent the true physics governing interstellar object behavior. The parameter estimation problem that emerges from fitting theoretical models to observational data reveals fundamental degeneracies that prevent unique determination of physical characteristics even when extensive data sets spanning months of observations are available. Object mass, size, shape, surface composition, internal structure, and rotation state all influence trajectory predictions in ways that partially compensate for each other, creating families of theoretical models that produce nearly identical orbital predictions despite invoking dramatically different physical assumptions about the object's properties. Bayesian analysis techniques attempt to quantify the uncertainties associated with parameter estimates by exploring the full multidimensional space of possible object characteristics that remain consistent with observational constraints. These statistical approaches reveal that current datasets provide insufficient information to definitively distinguish between competing theoretical explanations for anomalous acceleration behavior, leaving fundamental questions about interstellar object physics unresolved despite intensive observational and theoretical investigation. The propagation of uncertainties through orbital integration calculations compounds the parameter estimation challenges. Since small errors in initial conditions or force model parameters accumulate over time into large trajectory prediction errors that can exceed observational uncertainties within weeks or months of the final observations. This sensitivity to initial conditions reflects the chaotic nature of orbital dynamics under the influence of multiple perturbing forces, and yet it also highlights the fundamental impossibility of making long-term predictions for objects whose behavior cannot be adequately described using existing theoretical frameworks. Monte Carlo. Simulation techniques explore how measurement uncertainties and theoretical model limitations affect the reliability of trajectory predictions by generating thousands of slightly different orbital solutions that span the range of parameters consistent with observational constraints. These statistical ensembles reveal the full extent of predictive uncertainty associated with interstellar visitor trajectories, demonstrating that current mathematical models cannot provide the precision required for confident predictions of future positions or reliable reconstructions of past orbital histories. Machine learning algorithms trained on databases of solar system object trajectories struggle to identify patterns that might illuminate the anomalous behavior of interstellar visitors, since the small sample size of confirmed interstellar objects provides insufficient training data for statistical pattern recognition techniques. The exotic characteristics that distinguish interstellar visitors from conventional solar system bodies lie outside the parameter space spanned by the training datasets, making it impossible for automated analysis tools to extrapolate reliable predictions for objects that exhibit unprecedented behavior. Alternative mathematical formulations attempt to incorporate phenomenological force models that can reproduce observed trajectory deviations without requiring detailed physical explanations for the underlying mechanisms. These empirical approaches treat the anomalous accelerations as additional terms in the equations of motion with functional forms chosen to match observational data rather than derive from first principles. Yet even these flexible mathematical frameworks struggle to achieve satisfactory fits to the full trajectory datasets without invoking parameters that change with time in ways that resist simple mathematical description. The fundamental question emerges whether the mathematical failures reflect limitations in computational techniques and theoretical models, or whether interstellar objects operate according to physical principles that transcend the mathematical frameworks developed for describing conventional solar system dynamics. The persistent residuals that resist elimination through increasingly sophisticated modeling efforts suggest that humanity's understanding of celestial mechanics may be fundamentally incomplete when applied to objects that originate beyond the gravitational boundary of our stellar system. Quantum mechanical effects that remain negligible for macroscopic objects under terrestrial conditions might become important for exotic materials formed under different stellar environments, creating subtle but measurable deviations from classical orbital mechanics that accumulate over the months-long observation periods typical of interstellar visitor studies. These quantum corrections to gravitational dynamics remain largely unexplored in astronomical contexts, yet they represent potential sources of anomalous behavior that lie beyond the scope of current theoretical frameworks. The mathematics of the unknown sleep fitfully in computational databases filled with orbital integration results that refuse to converge toward observational reality, leaving behind equations whose solutions drift steadily away from measured positions despite starting from initial conditions determined with extraordinary precision. These mathematical failures serve as reminders that the universe operates according to principles that may transcend the comfortable boundaries of established theory, principles that remain encoded in the trajectories of cosmic wanderers, whose behavior challenges the fundamental assumptions underlying 3 centuries of celestial mechanical calculations. Through the vast emptiness that stretches between neighboring star systems, cosmic messengers drift on trajectories that carry encoded information about planetary formation processes, stellar evolution, and chemical enrichment patterns that operated billions of years ago in galactic environments whose characteristics remain forever beyond the reach of direct human observation. Each interstellar visitor represents a unique sample of materials forged in alien stellar furnaces, shaped by planetary accretion processes that unfolded under different conditions than those that characterized our solar system's formation, and subsequently ejected into the galactic medium through dynamical interactions that span timescales measured in hundreds of millions of years. The isotopic signatures preserved within these cosmic wanderers provide direct evidence of stellar nucleosynthesis processes that operated in different galactic neighborhoods, encoding information about the mass functions of stellar populations, the chemical evolution pathways of stellar disks, and the mixing mechanisms that distributed newly synthesized elements throughout the interstellar medium during successive generations of star formation and stellar death. These atomic fingerprints represent humanity's only direct samples of materials from other stellar systems, yet accessing the full wealth of information they contain requires analytical techniques that remain beyond current technological capabilities. Compositional data derived from spectroscopic observations reveal systematic differences between interstellar visitors and solar system objects that reflect either the diverse environmental conditions under which planetary formation processes operate throughout the galaxy, or evolutionary pathways that modify object characteristics during their millions of years of travel through the hostile environment of interstellar space. The enhancement of refractory elements relative to volatile compounds observed in several interstellar visitors suggests formation in stellar disks with different temperature structures than those that characterized the early solar nebula. The size distribution of confirmed interstellar objects appears dominated by fragments smaller than a few kilometers in diameter, suggesting that most cosmic wanderers represent debris from catastrophic disruption events rather than intact planetary bodies that escape from their parent stellar systems through gravitational perturbations alone. This predominance of small fragments implies that violent processes, perhaps collisional cascades, triggered by migrating giant planets or tidal disruption during close stellar encounters, play crucial roles in populating interstellar space with detectable objects. Velocity measurements for interstellar visitors encode information about the galactic dynamics and stellar kinematics that operated in their formation regions. Yet interpreting these data requires sophisticated models of galactic structure and evolution that incorporate uncertain parameters describing stellar populations, spiral arm dynamics, and gravitational perturbations from massive molecular clouds encountered during interstellar journeys that span hundreds of millions of years. The observed velocity distribution suggests ejection mechanisms that can accelerate objects to speeds far exceeding typical orbital velocities in planetary systems. The rotation states inferred for interstellar objects provide clues about the collisional and tidal processes that shape their final configurations before ejection from their parent stellar systems. The complex tumbling motions observed in several visitors suggest either formation through catastrophic fragmentation events that imparted random angular momenta, or subsequent modification through gravitational torques and collisional encounters during their lengthy journeys through regions of space where matter densities approach perfect vacuum conditions. Surface modification processes operating during interstellar travel gradually alter the optical and thermal properties of cosmic wanderers through mechanisms that include cosmic ray bombardment, micrometeorite impacts, and thermal cycling driven by encounters with stellar radiation fields throughout their galactic orbits. These space-weathering effects complicate efforts to infer original formation conditions from current observational data, since the surfaces accessible to spectroscopic analysis may bear little resemblance to the pristine materials that condensed in alien stellar disks billions of years ago. The apparent diversity of physical characteristics observed among confirmed interstellar visitors suggests either genuine variety in planetary formation outcomes throughout the galaxy, or systematic observational biases that preferentially detect objects with unusual properties that make them easier to identify against the background population of conventional solar system bodies. The small sample size of confirmed interstellar objects precludes definitive conclusions about the true diversity of cosmic wanderer populations, yet the observed range of sizes, compositions, and dynamical characteristics hints at underlying complexity that challenges simple theoretical models. Theoretical predictions for interstellar object encounter rates suggest that systematic sky surveys should detect dozens of cosmic visitors per year using current observational capabilities, implying that Oumuamua, 2I Borisov, and 3I Atlas represent the first recognized members of a vast population that has been streaming through our solar system undetected throughout human history. The recent identification of interstellar visitors reflects improved survey sensitivity rather than increased encounter rates, suggesting that interstellar space contains far more wandering debris than previously suspected. The chemical evolution implications of interstellar visitor compositions extend beyond individual stellar systems to encompass galaxy-scale processes that govern the distribution and mixing of elements throughout cosmic history. The isotopic ratios and elemental abundances preserved in these objects encode information about stellar yields, galactic chemical gradients, and temporal variations in star formation rates that complement but extend beyond the limited perspective available from studying only solar system materials and local stellar populations. Astrobiology considerations suggest that interstellar visitors might transport organic compounds and possibly even microbial life forms between stellar systems, creating mechanisms for panspermia that could influence the distribution and evolution of life throughout the galaxy. The organic molecules detected in some interstellar objects indicate that complex chemistry operates in diverse stellar environments, potentially creating organic inventories that contribute to prebiotic chemical evolution on planets throughout galactic space. The technological implications of studying interstellar visitors extend to future spacecraft missions that might intercept and study these objects during their passages through our solar system, providing opportunities for detailed analysis that could revolutionize understanding of planetary formation processes throughout the galaxy. Such missions would require rapid response capabilities and advanced propulsion technologies that could match the high velocities and unpredictable trajectories characteristic of interstellar visitors.